Welcome. Today we have the pleasure to host Dr. David Martinez-Delgado. David is well known here at the IAC because after the degree in physics in Madrid, he got his PhD here. And then he was also support astronomer for the Canarias Observatory. Later, his career has been between Germany and Spain. In Germany in particular, he enjoyed a humble research fellowship, and here at this IAC also a Ramón y Cajal. And since 2020, he is researchers at the Instituto de Astrofísica de Andalucía. So David is well known for his research in resolved stellar population, and in particular, he has an impressive record of discoveries, including the northern stream of the Sagittarius dwarf galaxies, new galaxies in the local group, and he has a long-term project in low surface structure, and in particular, he was pioneering in using also amateur astronomer for ultra-deep imaging. And currently, he's the PI of a project called Stellar Stream Legacy Survey, which I guess it will be the core of his talk today. So, David, thanks for joining us, and I give you the word.
Okay, thank you very much, Mateo. It's a pleasure for me to give this talk in my former institution. In fact, this project was born there 15 years ago. And now we are going to deal with a new chapter that is very exciting, because this project was at the beginning based only in amateur telescope, and now we will have the opportunity to put a small telescope in the space with the recent approved mission by ESA called ARRAKHIS. So I will try to tell you all the history of this project from the beginning. Also at the end of the talk, I will present some information about this mission that was approved only a couple of months ago. Well, the main question that we want to answer with this project is to try to find out how the galaxy like the Milky Way is formed. In fact, you know that quantum matter simulation predict that a galaxy like the Milky Way formed by the accretion of several hundred of satellites, or in this case, dwarf galaxies. And in this case, in this simulation, you can see different aspects in some prediction for dark matter, gas, and stars. So in this project, we are only dealing with the stars. So what evidence about the hierarchical galaxy formation we can get for studying the stellar halos, the substructure in the stellar halos? And this is very challenging because practically this means only to study the 1% of the total mass of the galaxy, right? So this simulation predict that the debris of this process of the accretion of satellites should be still in the halos nowadays. In this simulation, you see that how a stellar halo looks like currently. You go deep enough. This means that you expect a complex structure of debris. For example, in this simulation by Bullock, you see some color knots that will be the survivor galaxy. So the question is, we are able to detect these fossils of the hierarchical galaxy formation nowadays with our facilities. Without doubt, the most spectacular phenomena in this hierarchical galaxy formation is the formation of stellar tidal stream. You can see here that practically the accretion of a single satellite, single dwarf galaxy with the typical mass of 10 to the n, or 10 to the 8, or 10 to the 9 stellar mass is enough to deposit a very complex structure in the halos. At the end of this process, not only the star, also the globular cluster, the dark matter, are incorporated to the stellar halo of in our case, the Milky Way Eye galaxy. So this is the simulation that show very, very well this process. As you see at the end of this process, practically you start to see any current features in the halos. Practically all the destiny disappear as a mix with the stellar halo population. Well, these simulations are also an excellent field guide for stellar stream hunting. In fact, the first lesson that we learned from this model, and in fact, this simulation were the inspiration for this project, was that we should, practically all the Milky Way galaxies should display this kind of stellar debris if you go deep enough. The question is that when you, for example, when we started this project in 2005, the only available DIT imaging was from the Sloan Digital Sky Survey, and practically we couldn't see any feature in the halo. So practically this halo should like very smooth structure. So well, the lesson from the models say that the strings are really fine stuff. Only few features are brighter than 28 magnitude for square second, and the majority of the stuff are fainter than 30 magnitudes for square second. So this means that you need very deep images to try to detect them. And also, as you can see, these are 9 models. This is some old stuff that we have. I will show you more modern simulation later in this talk. Is that practically each halo looks like different, and this is due to the stochastic nature of the satellite accretion. Practically, you should expect a completely different morphology, a large variety of morphology of stellar stream, even looking at very few galaxies. And this is in fact what we find in our survey, as you will see later. So in short, what the model said was that the strings are out there, so we would try to find them. Also, what are the main motivation of why to study stellar strings are so interesting? Well, this is because they provide observational constraint in the local universe about the formation and also about the dark matter nature that lead this hierarchical galaxy formation. This means that we can get constraints about the galaxy assembly and emerging history of Milky Way galaxies in the local volume. We also can understand how this accretion process of satellites interfere with this evolution of these galaxies. This means how the cosmology affects the inner galaxy, even in galaxies similar to the Milky Way. Also, we can get constraints about the dark matter nature in the morphology. As you will see, the frequency of this stellar string will depend on the dark matter nature. It is called dark matter or dark matter. And very interesting, and it is not exploited yet because we have not good facilities for that. We need to wait for the next generation of telescope and instrument is to try to test stellar string at natural test particles in order to weight the dark matter halo of the host galaxies. Well, this is, of course, the natural place to look for a stellar string was the Milky Way. This was 20 years ago. In fact, this project was born, this topic was born practically with the first large-scale photometric survey, like Sloan Digital Sky Survey. And you can imagine why the stellar strings were so difficult to detect when we only had a very narrow field intermediate side telescope. It's a stellar string as seen from the Earth is practically a river of the star with a super brightness of 28 magnitude per square second crossing the full sky. First, the first evidence of this stellar string was the famous Sagittarius stellar string. Now it's practically a completely different topic. In fact, we did some of the first detection in the IAC more than 20 years ago. And well, this was a galaxy detected behind the center of the Milky Way at 25 kiloparsecs. If you are here, you will see in the bottom. Sorry, I cannot use the mouse, so you have to. I hope you can guide by my words. But in the bottom right, you see a spectacular view of the Sagittarius stellar string for Gaia. This is a stellar density map from Gaia, red clam stars, and you see as the collision of this galaxy with the Milky Way. And practically when we started to trace the stellar stream using embodied simulation with the INT in La Palma, we realized this is the view in 2001 that the stream is enveloping the full disk of the Milky Way, right? So this is maybe the most spectacular case of the stellar stream in our galaxy. So the question, and this was the motivation to try to find out at the beginning of this century, we can detect this stellar stream in other galaxies. In this case, we need to deal with diffuse light detection. In the case, all the studies in the Sagittarius stellar stream are made using the resolved stellar population. In our case, we need to deal with the very difficult task of detecting faint feature as faint at 26, 28 µ/s². So the strategy was rare because if we decide to use amateur robotics small telescope with the typical aperture of this telescope are 10 to 50 centimeters. Of course, we need a long exposure time, no less than 6 hours. And we use a luminance filter. This is not a calibrated filter. It's practically similar to G+R. And we use this photometry calibrated with airband SLAM data that is very, very successful. And here you can see some pros and cons of this approach. For example, here you see an example of the same galaxy with a small telescope and with a professional telescope. Well, the surface brightness limit is practically the same, 28, 29.5 µ/s. In our problem, as we use this luminance filter, we had not color, so we cannot derive information about the stellar population or stellar masses of this structure. We not did in our case with bright star. Bright star are not a serious problem, as is the case as you see below in the 3.5 meter telescope. We had less reflection, less scattered light. So because we are using very simple optical system, and our scene is not very good. It's mediocre scene, as best at 1.5 per second. So in comparison with a professional telescope, they had the advantage of get broadband photometry, but the main problem that they had is bright star, scattered light. The galaxies are so bright that they produce artificial halos, so they produce reflection. Of course, they had 2-second scene, but maybe the main advantage of all this is that practically one night in this telescope costs the full equipment that we are using in our project. So this is this is really, really cheap approach. But this is the typical telescope that we're using. As you see, we had the typical is redshift 10, 50 centimeter telescope, but also here you see, maybe you can recognize Isania, is we in some cases that we need wide field images, we use also apochromatic refractor with 10 centimeter telescope. In fact, we had published some astrophysical journal papers with 10 centimeter telescope because it's they go really, really deep and provide a large wide field view. Also, this is maybe one of the most difficult things now is to get deep size to undertake this ultra deep imaging. Particularly in Europe, it's very, very hard. Now we had one telescope in the Alps, but the majority of our facility were in these black holes in the United States. But this is the reason because the majority of our telescopes are robotic. They are controlled from homes of the amateur astronomer. And well, this is the greatest hit of our survey in the last 10 years. For the first time, we detect stellar tidal streams in nearby galaxies. In fact, when we started this project, only 3 stellar streams were known, but practically from photography plays taken by the famous David Mellin. And now in only 3, I think this is not a date, but I think we have discovered 50 stellar streams using amateur facilities. Of course, all these features are only traced by diffuse light and are completely different, for example, to this stellar density map of Andromeda. They accounted in Andromeda, practically what this is not an image, it's a map of red brown stars. So this means that in our case with diffuse light, we only can reach typical surface brightness of 29 µ/s. This is more or less 3-4 magnitudes deeper than the Sloan digital sky survey images that were the available data at the beginning of this project. Here's some comparison again in order to see how professional facilities in comparison with amateur data. I think you see, I already talked about the Canada French Hawaii telescope. Sloan, even stacking Sloan data is not enough to detect faint feature. Particularly, all of them are not there. And now maybe the most promising professional data of the DESI Legacy Survey. In fact, this is the data that we are using currently now, as I will discuss in the second half of the talk. And this is very interesting. The second one, the Subaru. The Subaru is, this is in the top, you see a stellar density map of red giant star. This is not an image. And below you see our image, the discovery of this string with our small 30 centimeter telescope. And it's very interesting because the map of all the stars is practically the same that the image of diffuse light image. So this means that these structures are mainly traced by all the stars. They are mainly composed by all the stars. One of the main problems that we had in our project is again zeros. In order to avoid this problem, we try to observe only target high galactic latitude, and in some cases this is not enough because practically when you reach superfluence 29 magnitude per second, you see zeros everywhere. So now with the new project that we're using professional data, we are trying to avoid to disentangle the zeros features from streams using colors, and also in some cases, if you had a white field, you can see its a feature is really associated to a large structure that is typically that is not consistent to be associated with the host galaxy, or even. But as I say, this maybe the main problem, that we had in this project, and it's very difficult to avoid it. We are still trying to dealing what is the best way to try to disentangle the stream from galactic zeros from our galaxy. Now I'm going to tell only some interesting results. Also during this last decade was the discovery of the first tidal stream in a dwarf galaxy. This is also predicted by cosmological simulation. I mean that dwarf galaxies also eat dwarf galaxies. So this the hierarchical galaxy formation process is also a smaller scale. In this case, this is NGC 4449. It's a galaxy similar to the Magellanic Cloud, large Magellanic Cloud, and it's eating something like a galaxy with the half of the stellar mass of the small Magellanic Cloud. We were really lucky to take super thin data with Subaru 8.8 meter telescope, and this was the first time that you can see the string like a river star. In fact, for me, it took me 10 years to see this view. In fact, this was a view that you only had in embodied simulation, and now you see actually a stellar strings of river stars. And it's interesting as when you build a stellar density map using this data, you can identify the progenitor. Sometimes if you look at the majority of the diffuse light feature images, you don't see the progenitors of this string. In some cases, it's because they are completely unbound. This structure are practically full destroyed. Or the other explanation is our scene is so bad that we are not able to disentangle the core of the satellite from the overall stellar string. Another interesting result was to find a globular cluster similar to Omega Cen as the nucleus of one of its stellar stream. This is an idea that Lindenberg suggested for the Milky Way, and it was confirmed also later. In fact, in the IAC, we confirmed that Palomar 12 was associated to the Sagittarius stellar stream 20 years ago. In this case, it's the first case that you see this phenomena in an external galaxy. This means that when a satellite is destroyed, also the globular cluster system is incorporated to the globular cluster system of the host galaxy. In this case, this galaxy, this is a very massive object, and this suggests that some of the most massive globular cluster, the Milky Way, like Omega Cen, could be of the external origin, could be ancient nuclei of the destroyed dwarf galaxies. In fact, we had already more cases. We are now writing a new paper with a similar case. So this is a new topic to try to detect a stellar string embedded in globular cluster embedded in a stellar string. You can see practically with Subaru, with these images, we got the Subaru data practically we almost resolve the outer regions of this globular cluster. This is also a very interesting case that is more recent. This is still in, I think it will be published in next month. We detected a blue stream. This is very rare because practically the majority of the stream are red, consistent with the whole population. In this case, this blue stream was the follow-up was made with Megara, and we find some emission. This is a very, very, very rare case that we need to still to explain, and this is in the context of the interaction of the stellar stream with the disk of the galaxy. So the question is, what happened with a stellar stream cross the disk of the host galaxy? Can induce star formation, or can this interaction induce a star formation episode in the core of the dwarf galaxy? So I think in this case, the best explanation for, I think it's still very preliminary, is that we are observing a star formation episode in the progenitor of the stellar stream. Also, one thing that is obvious when we look at our images are the large variety of morphologies that we observe in the stellar stream, and this is easy to interpret with embodied simulation. Practically, you can classify the majority of the stellar stream in three cases. One is the circular orbit, or the other one in radial orbits, and the mixed type that are practically destroyed. I would say mixed type is practically the end of stellar stream. When the stream is completely destroyed, you don't see any coherent feature. In this case, you see several. For example, in the top panel, you see practically the same orbit with the angular momentum component is 0.1. But in this case, you see different stellar mass, 10 to the 7th and 10 to the 8th. So this means that practically with the same orbits, in this case, is when you have this low value for the circular component of the angular momentum, you see a radial orbit. You see as the difference is dramatic, but depending on the stellar mass of the progenitor, you see different wraps and different envelopes. And also, it's the same case in the bottom panel. In this case, you had the circular angular momentum. The ratio between the angular momentum and circular angular momentum is practically 1. This means it's a circular orbit. And again, you increase the stellar mass from 10 to the 7 and 10 to the 8. This means that practically you see different wraps and different galactocentric orbits. So practically, you can interpret all these morphologies of the stellar stream with the tidal orbit, the tidal accretion, and the mass of the progenitor. The main problem is that in the majority of our cases, due to we have a surface brightness cutoff, you don't see the full stream. You only see the brightest part of the stream, and this made the interpretation of the morphologies really, really hard. But here you see the three types: is a circular orbit, and to the left, in the center, this is the gray circle. In the center, you see the shells or umbrellas. This is due to the radial orbit, and to the right, the mixed types. As they say, the mixed types is satellites are created more than 10 gigayears ago, and this means that practically it's completely destroyed, and you see only a cloud of debris surrounding the disk of the host galaxy. I must say that we are only observing a structure that are 3 or 4 gigayears old. I mean, they were created only 3 or 4 gigayears ago. Practically all the other structures were already dissolved, or they are too faint to be detected for our surface brightness limit. So I mean, what I mean is that these stellar streams are very recent events, minor merger events. It's interesting that practically all the morphologies that we detect in our survey are in the cosmological simulation. But here you can see gray circle, spikes, umbrellas, partial disrupted satellites, jump plumes. So if you look in this simulation, you can identify these morphologies. However, we don't see this complex structure of debris. We only detect as the best one stream per galaxy, or in the majority of the cases, because in our talk, in this talk, I only show in positive detection, but we had a lot of negative detection. So this means that the best case, you had 1 or 0 stream in our images. So what is the reason of this? Why we don't detect this complex structure of debris predicted in the simulation? In fact, this was the strong motivation to undertake this project. Well, the explanation is again the surface brightness cutoff. As I told you at the beginning of the talk, at the beginning of this project, we had this long digital sky images that are 25 magnitude per square second. The super brightness limit is 25. So if you put this super brightness cutoff to the simulation, 25, you get something like B. This means all the structure disappear. They are so faint that practically you cannot detect maybe one stream in I would say the 5% of the sample. So now with this amateur telescope, we can reach 29 magnitude per square second. So you put the super brightness cutoff, practically you detect the brightest stream in each halo, and in some cases you also have negative cases. So this means that even though we go 3 magnitudes deeper, this is not enough to detect the faintest stream expected in the halos, and it's not enough to detect this proof of the hierarchical galaxy formation. These are, for example, COCO simulation for many halos. Every panel is a completely different model. As you see, the large variety or emergent histories for that you can get from this model. And you see a very complex structure of the in this case, but this is the poor model. This means this typical model has a super brightness limit equivalent to 40 magnitude per square second. This is not realistic. We cannot reach this kind of, this will be a perfect observer. We cannot reach this limit. So as soon as you put some realistic super brightness cutoff, the view is completely different. For example, here we are going to put the super brightness cutoff of the Sloan 25, and you see practically everything disappear. This is the main limitation to detect and to get a statistical sample stellar stream. Because, for example, we had estimated that for the amateur telescope, the frequency of stellar stream is only in the 15% of the sample. This means that if you want to compile 100 stream, a sample of 100 streams, you need to observe 1,500 galaxies. This is completely unfeasible using amateur telescope. Practically any amateur is going to give you his telescope for this, and also we need dark time. So this means that in order to compile a statistic of the stellar stream, that is maybe one of the most interesting objectives in order to compare with the prediction of this type of theoretical model, we cannot do it with amateur telescope. Okay, so unfortunately, the second generation of large scale surveys is providing wonderful data, and this is the data that we are using right now. The project that we are leading now is the Stellar Stream Legacy Survey, and is based in the DESI Legacy Survey imaging. In fact, we had selected 3,200 Milky Way-like galaxies with redshifts less than 0.02. And the data that this survey is providing is as deep as the amateur data with 29 magnitude per square second, and it's already available. So we don't need to take data. It is only in the disk. So, for example, this is what we use at Legacy Pipe. Legacy Pipe developed by Dustin Lamb. And we are not using the public data. We are reducing the raw data with the spine. So, and here you can see as particularly you only need to do the field of view and the center of the galaxy, and then this pine line build a wide field image. Particularly all the lines that you see here are different pointings. So the Legacy Pipe composed and correct the background for all of them and made this image. In the top, you can see the images with amateur telescope that takes 10 hours exposure time, and below you see the result of our pipeline in only 10 minutes of CPU. So, and we had thousands of galaxies to study. So this is a completely new opportunity to get for the first time a statistically significant sample of stellar stream. And this is the project that we are currently undertaking. It started only a couple of years ago. Well, the data are amazing. So this is one of the most interesting cases. And also practically we get the same super brightness limit that the amateur telescope, but in broadband, no luminance filter anymore. So we can get colors, we can get luminosities, and also the scene is second scene. So in some cases, we see details that are not possible with the amateur telescope too. So with this, assuming that we are observing more than 3,000 galaxies, we expect to compile the first catalog stellar stream with 400, 500 streams. And of course, this will allow to do a comparison with the prediction of cosmological model. That is maybe the main objective of this project. We had some problems. First, one of the problems is that sometimes the streams, when the stream interact with the disk of the galaxy, they form some kind of plumes. We call these galactic feeders. And in this case, sometimes very difficult to disentangle some features around the host galaxy that are actually debris of that galaxy, or is material expelled from the disk. That is a galactic perturbation. In fact, one of the main objectives of this project now, because we had broadband photometry, to try to get a criteria to disentangle a stellar stream, that is debris of the galaxy, from galactic perturbation. But this is one of the things that could contaminate our sample. You see some here. You see several examples of the we see could be galactic feeders. In some cases, for example, look at the leg. Is quite similar to a stellar stream, but could be also a galactic feeder. It could be a spiral arm due to was perturbed by the interaction with a satellite. Well, here we see a comparison of the legacy survey data with several surveys, including for example, we see I told you practically we get the same similar sulfur brightness than Sloan. Also, you will see a comparison with the famous dragonfly, but we had estimated the sulfur brightness limit of dragonfly using the 10 by 10 R minis box that Nacho Trujillo suggested to the community, and you see dragonfly is not going as deep as the DESI legacy survey. It's not reaching at 30 magnitude for square second at all. So in summary, I think for the moment, the only data that could go deeper that DESI legacy surveys are data taken with 8-meter telescope like Subaru, or the survey that Nacho Trujillo is obtaining with large binocular telescope. I think it's called LICE. So, but I think the most important advantage of this project now is that we can explore thousands of galaxies that we need to take any data. All the data are already available. Again, some comparison with some surveys, for example, sulfur brightness limits for the Sloan is in the top. The amateur telescopes are more or less in the middle, around 28, 29. And the stream DESI legacy survey is also 29. And you can see here also a comparison with the future that are Euclid or LSST, that it could be, of course, will allow to extend the stellar stream survey to a lower sulfur brightness regime. To the left, you see an histogram of our sulfur brightness limits between 28 and 29. And for the first time, we are able to get sulfur brightness for the stellar stream. It's interesting to see that even though we reach 29, practically we only detect a stream between 26 27, 2 magnitudes brighter. So this means that if you want to go very, very deep in the stellar halos, you need to reach sulfur brightness limit as typical of 31 magnitude per square second. And this is very, very hard with ground-based telescope. And in fact, this was one of the motivations to try to put a telescope in the space, to try to avoid the sulfur brightness of the sky. That is the main limitation for this kind of ultra-deep imaging or for detecting faint structure around nearby galaxies. Also, we are really happy that we get also color for the stellar stream. And this is a paper by my PhD student, Juan Miró. It's very rare because the result is very rare because for the first time we compare the color of the stellar stream with the color of the survivor population. We got this from the Saga survey, and the color are different. So we see the stream are redder, We don't understand this yet. There are several possibilities. One possibility is that, in fact, we are observing the string are red because the progenitor, rather because the progenitor of this string are different than the satellites detected in Saga. Maybe they are more massive. The string, I mean, the progenitor of the string could be more massive. Another explanation is that there is a kind of systematic selection effect. This is because practically Saga only selects satellites brighter at 25 magnitude for a square a second. So this means that maybe they are only counting star bursting satellites around Milky Way-like galaxies. But again, we need more observation. As we are getting the full catalog, we had already 200 streams, and we are performing the photometry for all of them. We hope to get a new version of this plot very soon and try to understand what is happening. Why the color, what is the reason of this color offset between survivor satellites and strengthening around Milky Way-like galaxies. Well, now I'm going to talk a bit about the future, about what can we do. This is related about using a string to try to get some information about the dark matter of the host galaxies. And well, this is one of our objectives at the beginning of this project, but it's really, really hard to do it because practically we only had photometric information for this string. They are too faint to undertake any kinematical survey, at least even with the current facility, even with KET or BLT. We need to wait for the next generation of the streamer telescope to try it. So, but we have tried several things. One is to try to fix embodied models to the projection of the string into the sky. And this is useful because at least get some information about what is the initial, the time of accretion of the satellite, the initial mass of the satellite, what is the nature of the progenitor, to estimate what is the mass loss, and try to predict different wraps of the string that you can try to detect with deeper images. And in the majority of the case, the main objective was to try to understand if we are observing only the debris of one satellite or we are observing multiple strings in the halos. So I'm going to show several samples. For example, this is the NGC 1097. It was this stellar string was the first string discovered by Alton R in the 70s, and during 30 years was overlooked because some people suggested it could be an optical jet, but it cannot be an optical jet because it has not counterpart in X-ray or radio. So I think the best explanation was that it was a debris of a satellite or several satellites. As you see, it's very, very rare. It has this L shape to the right. You see this L-shaped feature that's very difficult to explain. In fact, in some cases, I suspect it could be an artifact. But these images taken with a 50-centimeter telescope confirm all the features detected by Alton R in the photography plates. And in fact, we try to fix this by fitting more than 1,000 models to the image and subtracting each model from the image. So in this way, you can try to with the normalized residual to try to explain what is the best possible model. And the result is very interesting because practically it's impossible to get a good model if you don't include rotation in the progenitor. Particularly this L-shaped features is not, you cannot reproduce it, you don't include this rotation. This means that sometimes orbit, time on accretion, or mass of the satellite is not enough to reproduce all the morphology. In this case, you need to include something else, like the kinematic of the progenitor, right? So in fact, you see that you can fix all the feature with a single satellite with 3 pericenter passages. We in fact identify the progenitor. This is also a very important information that you get from the models. And finally, if you practically include rotation, you get a residual there. That is mean that the L shape cannot be reproduced with the titled orbit or you need an additional parameter for that. This is an example that trying to get a model using the projection on the screen onto the sky only without any kinematic information. When we can get kinematic information? Well, as I say, it's impossible to guess radial velocities for the diffuse light feature. They are the typical, as you see in the histogram, is 26. There is no telescope to reach this kind of to get velocity for so faint features right now. So the only opportunity is to try to detect dynamical traces embedded in the string. This is in planetary nebula or globular cluster. But this is a very expensive project that sometimes it doesn't work because you need a massive stellar string to have enough number of globular cluster or enough number of planetary nebula. And we undertake this with the umbrella galaxy. As I said, first you have to go to Keck telescope to get the narrow band photometry to identify globular cluster planetary nebula, and then you need to come back to do the spectroscopy to disentangle background object from this object, from this dynamical tracer. At the end, all this information is used as input to build an embodied model. As I say, this is possible only for a few cases. It's really, really expensive and time-consuming. So this is not an opportunity to try to get the stellar mass, the dark matter halos of the galaxy. So, however, I think in the next generation of telescope and instrument like Mosaic or Harmony, it will be the golden era for doing this kind of studies. Here you can understand very easy as what I mean is practically getting radial velocities, the radial velocity distribution across the string is sensitive not only to the total mass of the dark matter halo, it's also to the shape of the dark matter halo. Right? So you see the radial velocity distribution change when you change depending on the dark matter is oblate or spherical, and also the total mass that you include. So with Mosaic, for example, using Regent-Brandt stars, we hope to try to do this study to get radial velocity for a few hundred stars using the calcium triplet with typical resolution of 5,000 and signal to noise 30. But I say maybe only 5 or 10 string will be in the local volume to try to do this study. There are not too many, but at least we could extend the type or kinematics to a study that people is doing now in Andromeda. Okay? So I think the impact on Mosaic or Harmony in this topic will be huge. We are looking forward to this instrument. Well, as I told you, practically from the beginning of this project, we understood that the main limitation for detecting a stellar string and to go deeper and detect this complex structure of debris in Milky Way galaxy was the superbrightness of the sky. So the only solution was to try to put a small telescope into the space. So Rafael Guzmán, María Ángeles Gómez Flochoso, and me during the meeting in the Spanish La CEA in 2010, we had the idea of try to write a proposal to put this kind of telescope. It's a small telescope in a low orbit, and now this project was approved by ESA as a fast mission to be launched in 2030. Well, this is a consortium between different countries. And you can see here the main composition of the core team and the countries that are also involved. The IAC is also in the Spanish consortium. So, well, the main idea, as I said, is to put a small telescope in a low orbit, and our sample will be 10, 100 or 150, depending on if we get extension for the mission. Milky Way like satellites. In fact, the main topics, the main scientific case for this mission are stellar tidal stream, satellites, and also intrahalo light. But the idea is to get 150 hours per galaxy And I think the super brightness, we had already a simulator. The telescope is a binocular. There are two binocular telescopes. I think you can see here. This is not, it's only, no, it is not confirmed. But I think it shows more or less what is the idea is we have two binocular telescopes, one for the optical and one for the infrared. And this is some of the first simulation that we had from ARRAKHIS observation. We had to include all the ingredients, and I think our estimate, this is still preliminary, is that in optical we will read 30 magnitude for a square second, and the most important thing in infrared we will read 30 magnitude square second. This will maybe one of the most interesting things of ARRAKHIS because we cannot get infrared observation with this stellar stream from the ground. And this is fundamental to try to estimate the stellar mass and of these minor mergers. So here you have also a simulation in the optical, and I think with this, for the first time, we will hope to detect the faintest structure in the debris as expected in the cosmological simulation. As I told you, from ground-based imaging, we only can detect the brightest string in each halo, and this will be a wonderful opportunity to go deeper in the halos of the Milky Way, and also to try to put in context all the results that we are obtaining in the Milky Way with Gaia in more galaxies in the local group, and try to understand if the imaging history of the Andromeda or the Milky Way are typical or not. Okay, so I think this is the end here, the conclusion. I think it was practically. We are still in, this is a very young topic, we are still in the discovery phase, trying to get for the first time a statistical significant sample of stream to try to understand if there is tension with the cosmological model or not. But the future is bright. First, because we will have spectroscopy facilities to undertake kinematical studies of the stellar stream and try to use them to trace the dark matter halo of the host galaxy, and also to try to put a small telescope to try to make a similar project like this amateur project that I show in my talk from the space. So I think it's as I take the next decade will be maybe the golden era for this topic. So thank you very much for your attention. I hope you had some questions. Bye.
Questions?
Hello.
Hello.
Maybe you mentioned this and I didn't get it. I have two questions. So what is you will detect the stellar streams with the DESI legacy survey up to which distance? I
think, yes, I told you that the sample is selected to be, the redshift limit is 0.02. We are only interested in a string within 100 megaparsec, okay? Because at the larger distance, we had also contamination even in the local value with post-merger. So I think if you go at a larger distance, to the discrimination between post-merger and this minor merger is more difficult. So we are only interested in a string within 100 megaparsec.
Okay, and this might be a very basic question, but when you observed this photometric image you show one image of this galaxy from the 70s with this L-shape stream. How do you know that the stream is part of that galaxy and not any other feature? So how are you sure when you are observing?
Well, I told you that there are two sources of contamination in our sample. One is the post-merger, okay? That this is a major merger that are now in they are very old and you cannot disentangle the two nucleus of this interaction. And the second is these galactic feeders. So these are they are galactic perturbations. So in fact, this is one of the objectives of this project is to try to understand or to look the criteria to disentangle between these three things. In some cases, it's easy using color and super brightness. In practical, for example, post-merger are brighter than minor merger. The majority, in fact, if you put a super brightness cathode of 25.5 to the feature, practically you had all your features are associated to this reaction of dwarf galaxies. And for galactic feeders, it's more difficult. I think the only thing that you can do is could be a cutoff in galactocentric radius, but this is something that we need to investigate it. So taking into account this is the first time that we are doing this kind of catalog galactic feature, so we are still need to understand this kind of selection effect.
Hi, David. Thanks for the interesting talk. It's Giuseppina.
Hi, Giuseppina.
Hi. I have two questions. So earlier in the talk, you showed there was a distracted satellite in which you were detecting very blue colors and also H-alpha emission.
This
and
one.
that, yeah, I think this one. And you said that this was a star formation induced in the process of the tidal stripping. So the question is, how can we distinguish this hypothesis from this satellite just being forming stars on its own and then being disrupted?
Yes, I think that there is no way. I think the question, this project, what we try with this project is that maybe this is not the most interesting case. Some years ago, we detected a similar case, but it was overlapping the disk. So it was not clear. We were observing a complex star formation due to the induced by the string interaction in the disk, or the progenitor with a star formation episode. In this case, I agree. It could be an induced star formation due to the interaction with the string with the galaxy, or simply a galaxy with a star bursting galaxy being disrupted. I think it's very difficult to know. I agree.
Thank you. And then the other question was, have you quantified or have you looked in detail to what would be the niche of harmony for helping with the kinematics of streams?
No,
the tiny field of view.
In fact, this is an email that I had to send you soon, because I would like to discuss this with you. So thank you for mentioning that. Yes, I think in fact harmony will be earlier than mosaic. So I think we need to try to understand what can we do with harmony first. So in fact, I have plans to talk with you about this.
Okay, thank you, David.
Hi, David. This is Carlos speaking. A related question to that one asked by Giuseppina. Is there any plan to systematically attempt to study the impact of these tidal streams or these mergers on the star formation history, or in the metallicity, or in the astrophysical properties of the galaxy? Like now you are having a first sample of objects where you have detected these tidal streams. Are you thinking of maybe in the future doing some statistical analysis on how this, whether this accretion, whether there's any possibility of connecting this accretion history with the actual?
Of course, it is a great idea. And I think what we need to compile first is the first photometric catalog of the stellar stream, because as I told you, practically only 10 years ago, we only had a sample of 20. So this was a very poor statistic for doing any study. So as soon as we had a few hundred, I think all this kind of studies can be undertaken. And in fact, it will be very interesting to check it. There is some relation between the property of the host galaxy on the star formation rate in the host galaxy with this kind of string, the stellar masses of this string. I think it's a really, really interesting question. But as I told you, one of the questions that we would like to understand is what is the effect, if there is any effect when the string, for example, cross the disk of the galaxy. We were looking at this some years ago, and it was very curious because we couldn't find any model to do prediction about that. So are the disks of the string are the disks of the galaxies transparent when to the passages of the stellar string, or no? There is some kind of induced star formation. I think this is an open question. And for the moment, we have not an answer. We start to have some few cases that could be interested in this context, but we still need simulation to see what is happening. Maybe some people looking at cosmological simulation can find, if you see, for example, one question is a string can form when a complex star formation in the disk of the host galaxy during the cross of the string. for the galactic plane. We try to look at this as I told you some years ago, and we couldn't produce this kind of complex. What we produce something more, the star formation more distributed along across the disk, but you cannot get, for example, a bluff of the star formation due to the collision on a string with the disk. This is what we wanted to find out or not.
So, David, thanks for the nice review. This is Jorge Sanchez. And I have a question which is connected to the first question of Josepina. It's about whether, from theory, you expect to have the same streams in gas, and whether that thing can be observed. I guess they should be also. They are in gas, but they are probably very hard to see. Could you comment on that?
Well, the problem is in gas, you have the ground pressure, so the kinematic is completely different. And also, practically, we have not found any gas counterpart in any of our streams. So this is one of the problem is that practically, for example, the gas, in the stellar stream, you had a leading and a trailing arm. However, for example, you take in account in gas only, you see only a leading tail, so a trailing tail. It's like a comet. Okay, so it means that the kinematic of the gas and the kinematic of the star is completely different. And also, we have the problem with the detection of the gas in this structure. For the moment, we only had one case. This is this one, but we published a paper last year, and this is the only one where we see the gas is practically is very consistent with the distribution of the star. And maybe this is because we are observing the formation of this star stream right now. It's very close, but in the majority of cases, this kind of study with gas is not possible. It's not feasible. So you need to go to get the radial velocity of the individual stars, and this is only possible with the next generation of telescope for the distance of this object, this system.
Okay. And I have, well, can I continue? It's more a comment than a question. Maybe I misunderstood you, but you say that the colors of the satellites and the streams are different, and this is partially. To me, it's very natural.
Say again?
That the colors of the satellites, galaxies, and the streams differ. So streams are red. But this
we are still at the beginning of this project. I mean, for the first time, we could get colors. As you see here in the bottom, it was our first opportunity to get accurate colors of this structure. And then you had this survey that is called satellites around Milky Way galaxies called SAGA. They are selecting the satellite using Sloan, and they go to Keck to clean the samples, okay? Because when you do a photometric selection of the satellites, you put some color cutoff, but in any case, you always have some kind of background contamination. So in order to get a bona fide sample of satellites, they go to Keck and get the radial velocities for this object. No? So practically, what you had is a sample of satellite that you are completely sure they belong to the host galaxy, right? Well, when you compare this, the color of this satellite, this sample of satellites, with the color of our stream, you clearly see a difference. The satellites are bluer. The survivor, the typical survivor of this hierarchical galaxy formation that you observe today around Milky Way galaxy seems to be bluer than these streams that are galaxies.
This is what I understood. But to me, it's very natural. That's what I was trying to say. Mm-hmm. Because the streams, I mean, when you quench star formation in a stream a few giga-years ago, you told us about the time scale. So of course it's going to be red, whereas the satellites still form stars now, and they have to be blue.
Well, some of them form stars, but you also know the dwarf-spheroidal galaxies orbiting the Milky Way are also red because they stopped forming stars 10 giga-years ago.
Yeah, but I presume.
So I think it could be a problem not selection criteria. Due to they are selecting satellites to go to get for a spectroscopy, they put a sulfur brightness cutoff in the sample of 25. This means that maybe they are only selecting this galaxy, the galaxies that you mentioned, the galaxies forming a star right now. However, galaxies like Draco, Carina, Ursa Minor are out of the survey because they are fainter and they cannot get a spectroscopy.
Yeah, but what I was saying is that,
explanation. But
I mean, if you take a sample of satellites, some of them will be quenched, some of them will start forming now. So the average is going to be bluer. The streams that are all quenched.
Yeah, this is what we, in fact, we are looking at cosmological simulation right now to see if we see this difference between both of them. But there are several, it's possible that this is a real difference in the stellar population or color. There is an explanation for the different related with stellar population different, but it's important taking account that it could be also a selection effect. We need to understand this better. And this is because this is only a letter, and now we want to repeat this with a larger sample, more than 100 streams, and we will see. Also, Saga is getting more and more data right now, so I hope in a few years we can do the same plot with more statistics and see this different remains.
Well, so David, it's also to comment that if you take the Milky Way or Andromeda with your, you were saying that you were just selecting basically or detecting the most massive streams. So if you take the Milky Way or M31, you're going to detect the giant stellar streams, Sagittarius, Cetus, but all of them are redder than the average distribution of the dwarf galaxy as well.
I have to clarify one thing. If you put Sagittarius or the stellar stream on Andromeda at this distance, they cannot be detected in our project. They are too faint. All the streams in our sample are more massive than the stellar stream detected in the local group. In fact, this is something that I'm working with Jaume Thomas here in the IAC. We are injecting Sagittarius models in the DESI legacy survey images, and practically the preliminary result of this project is that Sagittarius cannot be detected with diffuse light feature from the ground in the local group, in the local universe. So they are too faint. All the stellar streams that we detect in our project are brighter and more massive.
But it's what was meaning that the progenitor is also more massive.
Yeah.
Might also explain why you are redder, because you are more metal-rich in average as well.
Yeah, I think one thing could be that, as I told you in my talk, that the progenitor of this string are more massive, and this is the explanation of the string are redder. This could be also an explanation.
And I have a last questions. Since now you have the colors, can you also use them to identify some streams that might be coming from the disk, like the ACS in the Milky Way, so that have been kicked out from the disk?
You mean these things, the galaxy feeder,
galaxy,
like this one, or I don't understand very well?
Yeah, like this one, yeah.
These features, yes, I think we clearly see several features that are consistent with the galactic perturbation. The question is, as we have now access to photometry, can we disentangle the stellar stream that is tidal debris of our galaxy from colors or not? This is a very interesting question that we have no answer yet. If they overlap in color, it's going to be very difficult. We will expect different colors if it is material from the disk, but we don't know. I hope we can get some answer of this soon, because otherwise we will have a contamination of galactic feeders in our sample.
Okay. Well, thank you very much, David. Is there any other question? Okay, so let's thank David again.
Okay, thank you very much.